So let's go ahead and I will share my screen. Lorelei, it's a great picture. I'm digging it. Let's see, we don't need this up. Let me move some of this stuff over. Cool. All right. So let's go ahead and go through the canvas for the class. Again, if you were with me last quarter, pretty much the same as it was last quarter. But let's go ahead and talk about things. So this is Co16B, spring 2021. Class meets from 9 to 10:20, Tuesday and Thursday. That's right, Tuesday is TR is Thursday, so Tuesday and Thursday. My office hours, I guess I'll start having office hours today, yeah. Monday, Wednesday, Friday, 9 to 10 and 2 to 3, as well as Tuesday and Thursday from 11 to 12. The link is there. The password, as I'm sure you all are aware, is mute. If you're here, it means you probably know the password. I assume it requires the password. I don't actually know, so maybe you can just come in without putting it in. I don't really know. I'm the instructor. You can call me James. You can call me other things as well. If I understand not wanting to call your teacher by their first name, but you're welcome to call me James. Really, that's what I prefer to be called. But if you can't stomach that, I mean, not that you guys are saying my name all that much, right? There's not a lot of talking going on, other than from me mostly. But if you want to address me in email, James is fine. Mr. Parmenter is also fine, but it sounds way too formal. Let me get the chat up. Okay. Yeah, maybe I need to change the setting. I'm not super worried about right. I mean, I know at the beginning of all the Zoomness, there was the Zoom bombing. I feel like it's not really a thing that's happening anymore, but that's why we had passwords. So some people said they didn't have to use the password. Oh well, I'm not too worried about it. But thanks for letting me know. I appreciate it. Let's see, my email's there. Email is usually probably the best way to get a hold of me. Definitely am pretty good about responding relatively rapidly. That's my phone number. If it's an emergency, call me on my phone. Emergency being, I mean, really, I had that more for my for the class I was teaching last quarter for pre-16 because I was actually giving them exams, and occasionally a student would have an issue trying to upload an exam in the time allotted to them. But if for some reason you feel like it's urgent that you must get a hold of me right away, you are welcome to call or text me. But really, email is probably best. And then there's also a link to the discussions. I just have that up because I really would like to encourage you all to use the discussions. So I've already used the discussions. I'm sure many of you saw. I asked if anybody had info for either Ma or Lee. I should get on those Discords, by the way. Not that matters to you guys. I will try to be. I forget what my class times are, but if I know I had scheduled for myself. Let's take a look real quick here. Did I schedule that? Let's see. Let's look at my schedule. You guys can see my schedule. It's very exciting. It's not exciting at all. Oh, it's super blank. I think I had intended to sit in on one of the classes. Let's see. Sitting on the 17Cs. Yeah, I plan to on Monday, Wednesday, and Friday from 3 to 4 sit in on Ma's 16B class. So I will try to be in there, and I will attempt to be on the Discord if you, and you guys could always ask me questions if you want, or each other, right? Anyway, just thought I would mention that. So, but yeah, I would say discussions are a great. Sorry, leave the water. Dying. Okay. I think discussions are a great place to interact with each other and me. If you have questions about math, it's a great place to ask them because then other students can chime in. I will also often chime in and give guidance or just straight up answers, depending on the context. But it's a great place to ask because then everyone else can also see the answer. So I would really encourage everybody to, if you have a math question that you want to ask me, ask it in the discussion instead of in an email. I will happily respond to either, but if you do it in the discussion, it really gives everybody the opportunity to see the fruits of our labor. So I will keep stressing discussions as much as I can. Try to use them. I think they're a good. I know there's lots of I know there's other places to do things as well, but for our class, this is kind of the venue we have. So use it. Let's go back to the syllabus / right. The homepage, the syllabus, same place. Some notes about the co-class. This is just kind of how the class is graded. It's a support class for people in 16B. Each class I'm going to show you stuff as we did. I mean, it's going to be like last week. but I will do examples mostly. Occasionally, I might have you guys work on stuff and then check in with you, but that is usually something I do more in person than online, right? It feels kind of weird, like, okay, you guys work on stuff, and I'm have you work on stuff when I use the restroom. As I'm sure you're well aware, I'll probably need a bathroom break in the middle of class. I will post the lectures after class, so you can watch them later if you want, or if you hadn't missed a class, also you can watch it later. Classes pass and passing grade is 75% or higher. 50% of your class grade is based on attendance of the Zoom meetings, and we'll talk a little more about that in just a second. 25% of the grade is based on completing the weekly reflections, which we'll go over in a second. As long as you do it, you get full credit. And then 25% of the class is based on completing the weekly quizzes. Again, as long as you do them, you get full credit. The grades are based solely on whether or not you complete them. As long as you do it, you'll get 100% of the points. And then I will still grade the quizzes and give you feedback. So you might get everything wrong, get 100% of the points, and get a lot of feedback about like, hey, this is what you should have done, or here's another way to look at it. So if you're looking for more, well, I mean, if you're enrolled in the class, you definitely need to do these things. If you're not enrolled in the class and you're just added to Canvas, you don't actually have to do any of that stuff. I still recommend doing it because I think it is worth your time, especially the quizzes, because I will definitely grade them and give you feedback on them. I will usually almost always post solutions to them as well. But definitely, I recommend doing them so that you can see some of your work graded in a relatively, like usually I grade them within the week, so they get graded pretty quickly. But you do have to actually go look in Gradescope and see, look at what comments I have written that I've clicked on for your particular graded quiz. As far as attendance, I do keep track of everyone's attendance, whether or not you're enrolled in the class. For those of you that are actually enrolled, attendance is part of your grade. If you do miss classes, you can make up some of those missed classes up to a maximum of 10 by just watching the video for that particular class that you missed and then emailing me that same week to let me know that you've watched it. I do want you to email me that same week that you watch it, just so that we're not at the end of the quarter and someone's like, hey, James, I just watched 15 classes. Can I get that? No, we don't want to do that. I want to keep the attendance relatively up to date and not have people at the end trying to cram in a bunch of things. Again, it's only one unit, it's workload. So for most people, it's probably not making or breaking whether or not you're full-time. But I know for some people, it might be like, I need this unit to make sure I'm a full-time student. If that is you especially, then you need to make sure you pass the class. So yeah, speaking of the unit, it's one workload unit. It does not apply towards graduation, but it does apply toward being full-time status for financial aid and visa status, as well as minimum progress. Again, harping back on the discussions, you can use the discussion tab, I should have linked it there, in Canvas to converse with each other, as well as ask questions, especially if you want me to see the conversation / question and have the ability to chime in. So again, use the discussions, they're pretty great. All right, a few notes about the class. This is kind of some boilerplate stuff. So each unit in the course is connected either directly or indirectly to the other stuff, meaning, the class builds upon itself. If you're not getting the big initial stuff, it's going to be harder to understand the later stuff. So we really have to constantly kind of work at making sure we understand what is going on. Successful students are usually spending 10 to 20 hours per week doing homework, practice problems, and studying for math. It could be more, it could be less. I think that's the Carnegie rule of some number of hours per unit. So definitely you should be spending time doing stuff. This is some of that time. The more you practice and ask questions, the more successful you will be. Get help. Obviously, you're already here getting help, right? This is help. But you might want or need or desire more help. If you do, there are certain places to get it. You can always come to my office hours. That's probably one of the easiest places to get direct help, because I am there in person, on Zoom, able to hear your questions and answer them right away, or guide you to the answer, or help you figure out what you need to be thinking about to think about how to find the answer. And then you can also send me an email or write a discussion. And then there are also other math specialists, Casey, Claire, Duff, Grant, Sarah. These are all links to their websites. You can get help from each of them in various ways. If you are looking for other help outside of me, which is perfectly fine, not be offended. Everyone's great. You should definitely use the resources available to you. There's also student tutors in the online drop-in. I feel like this is written weird. You can get help from a student tutor, an online drop-in, or that's supposed to be or a one-on-one appointment. Okay, that's fine. And you can find that information at this link. I don't think the drop-in is live until next week, but I'm not 100% sure about that. So you should check it out. You can also, and there's, yes, Marshall, there's also the calculus room. Excellent point. I thought I used to have that written on here. I don't feel like I do. There's also the calculus room. So you guys definitely make use of the calculus room if you wish. Here are some other resources. There's the AATC website, which has the classes and also the tutoring stuff. There's Grant's website, which I encourage everyone to take a look at. I often pull examples from here. I feel like a 16B has a little less, but there's lots of handouts about various topics that we will cover out throughout this quarter. And there's also my website, which is not particularly useful, but does have a picture of me and my cat. Speaking of which, she went out. Has all the ways to get a hold of me. It also has this link here where you can make an individual appointment if you want to. You can make an individual appointment with just me, or you can even bring along a friend, like it could be 2 of you and me. So if you click on that, it'll take you to Calendly, where you can schedule a half-hour appointment with me during some time of the week where I'm available. It also has the links to the classes and the office hours, but I figure most of you are probably accessing that through Canvas. Yeah. So it's been a whole week of not talking as much as I usually talk when I'm teaching, so I can feel my vocal cords are like, oh, I'm talking a lot. I'm feeling a little tired. Talked a lot yesterday too. Let's see. And then, yeah, so that's all that. Let's go ahead and talk about the assignments, specifically the reflections and quizzes. So if you look at a reflection, they're all pretty much, let's look at the first 2. Close this. Yeah. So here's what you're going to be doing in the reflection. I want you to include the following things in the first one: your name, your preferred name, hometown, something about yourself, what you went over in. So the thing that's going to be constant is this one, what you went over in your 16B class this last week. And I think in the next reflection, I'm a little more specific. A very brief summary of what you covered in Math 16B lecture on Monday, Wednesday, and Friday. So just, it's an opportunity for you to think about, oh, what did we do this last week, and kind of really give thought to that. And then you always would love for you to ask me a math question, or, and I've started thinking about this as well, instead of asking me a question in the reflection, you can say, James, I'm going to start a discussion, and write it there. Jokes, you guys sent me some pretty great jokes, memes last quarter. Keep it up. I really appreciate them. They do brighten up my day. It's okay if you don't have any, but if you have them, bring them. I like them. And then usually every week I ask you to tell me something not super personal about yourself, but just to kind of get to know people. If you really don't want to do it, you do not have to do it, but I would love for you to do it. I did change them this quarter, so they're mostly different than they were last quarter. So for those of you there that had Co16A, the reflections will not be exactly the same as they were last quarter. And that's a weekly thing. I think it becomes, let's see, this one is available April 8th, which is what? Tomorrow, it's a Thursday. So it's available April 8th. It's due April 12th, which is, I think, the Monday. And then it is available up until the 15th. So if you can turn it in late, I prefer you turn it in when it's due. But sometimes I know things happen. This is also good for me to read, because then I have an idea of what you guys are wanting to see during the week. So doing the reflections really helps me prepare for class, in that I know what to be thinking about to talk about. Like today, I'm like, what are we going to do today? Talk about exponential functions? I don't know. You guys have other questions? Maybe. So next week, you guys will be like, oh yeah, we have questions about this. Like, great. Like, I know what I'm going to be talking about. So please do those. And then there's also going to be quizzes. The weekly quizzes. Let's take a look at this one. This one's available. Oh, do I have a link already? Let's see if the link is live. I don't really think it's live. Oh, maybe I did. I put a quiz up already. Look at that on top of it. So here's the quiz. You can see it right there. This is really just, so this was kind of a reflection on how derivatives work. You know what? Actually, I feel like, no, this I might need to modify this quiz. I feel like this quiz might be a little ahead of the game here. So this quiz shouldn't be available yet. Let me double check and see. Let's see if I edit the assignment settings. Is it available yet? It is not available yet. Good. Okay, so you can't access this quiz yet, although you might be able to in Gradescope. Let's take a look at Gradescope. Let's go to Gradescope. Why am I not logged into Gradescope? That seems really silly. Sorry, one moment. I didn't hit the remember me thing. That's why I'm not logged into Gradescope. Anyway, if you look at now, there's nothing here. Cool. Okay, so I will get that quiz to be correct. I feel like it's a little further ahead than where we should be at. But back to the quizzes for just a minute. So you take the quiz, so it'll be available Thursday-ish. You can look at it here. It will be in Gradescope as well. You can look at it in Gradescope. Either way, do the quiz, write it on. You can either use a tablet, you can write it on a blank piece of paper, and scan it and upload it. Once you have taken the quiz, upload it to Gradescope, and then you should assign questions and pages, meaning let me know which answer goes to which. Most of you will probably write it all on one page, so you just be like, okay, there's one page. And yeah, I mean, the quizzes are not meant to be super hard. They're meant to just kind of test, maybe not test, even really give you an opportunity to practice doing the things you've learned that week. So I try to make them pretty relevant and not too hard, but somewhat hard. Like, I mean, I don't want them to be like super easy because it's an opportunity for you to do a thing. Yeah, definitely the talking. You got to remember how to talk a lot. Last thing, I think, let's see, discussions. Sometimes I'll post announcements. Usually it'll be like, hey, the quiz is available, or I don't know, I posted this one. If you're in Code 16 last, right? I always forget where to click up there, right? Here's me telling you what I was going to do today. You don't probably look at attendance. You can find files. I don't think there's any files to look at right now. There's uploaded media. I don't think you guys know. Oh, and lots of quizzes. All right. Those are probably the quizzes I gave last time I taught this class. And then let's look at the modules real quick. Modules is probably where you'll find most of the stuff that aren't assignments. So this top module here, you can't see right now. It's the course evaluation. This will become available near the end of the quarter so that you can fill out the course evaluation. There's nothing in the modules yet. After class today, I will upload the Zoom class video in the module right here, and you then can watch it if you want to. I don't know why that's not true. I mean, I can see why, to be like, hey, what did he say there? Okay. I also post the quizzes and quiz solutions here, and any useful handouts down here. So again, none of these things have anything in them yet, but they will start to very soon. All right, I think, as far as I can tell, that covers all of the kind of business of how the class works, or the administration of how the class works. You guys have any questions? Certainly fine if you don't. I just want to give you an opportunity to ask them if you got them. Oh, cool. That's what I thought. Lauren's like, I'm speaking for everyone. No questions. All right. Yeah. I mean, right. It's the same. So for those of you that were in the Code 16A class, it's the same damn thing we did last quarter. Just new material. All right. So that said, I guess we should start talking about exponential functions and logarithmic functions. And gosh, like there's kind of a couple. I kind of want to jump in and talk about those derivatives, but I know that's not exactly where you are. There is one thing I do. Yeah. So yeah. Okay, we'll talk about exponential functions briefly here. We'll probably get into logarithmic functions as well. And then I was looking at the notes from Lee's class, I did notice one tiny mistake. It's not a huge deal, but I do want to point it out because it is kind of a small deal. So let's talk about exponential functions. Yeah. And let me modify. Let me change my. Let me pin my video. Let me change my video settings so that it's a little bit easier to see the board. So hopefully making it darker like that usually makes it easier for everybody to see the board. You're welcome to ask questions via the chat. You're welcome to ask questions by unmuting yourself and saying words. You are welcome to use the reactions like the thumbs up or the raise your hand one if you have a question and you don't want to just start talking. I'm mostly cool if you just start talking, but if I understand also not wanting to do that. So if you don't want to do that, it's cool. I'm going to lower my hand here. I don't know how to turn off the thumbs up. Maybe it'll just go away. Could we do a review of log and natural log rules strategies at some point? Sure. Yeah. Sure. See what time it is. 9:20. Okay, we got about an hour. Let's do it. So let's talk about exponential functions. And I should say, when we talk about exponential functions, in some sense, we are kind of talking about logarithmic functions, not because they're the same, but because they're actually inverse functions. So a lot of the things that apply for exponential functions kind of in an inverted way apply for logarithmic functions. I know that's not maybe super useful, but they are very much related to each other. So let's go ahead and let's just jump right in. I want to look at this function, f of x equals 2 to the x. It's an exponential function, and it's called an exponential function because the exponent is a variable, right? That's the thing that makes it exponential. The base can be any number that is non-zero and non-negative. So positive and not one. So this is an exponential function, and it looks like this. Sometimes we plot points, right? Like you could say, okay, like sometimes, okay, we'll plot some points. So usually we just kind of like to draw the shape, but we can plot some points. We can do x and 2 to the x. If x is 0, 2 to the 0 is 1. If x is 1, 2 to the first is 2. If x is 2, 2 to the second is 4. If x is 3, 2 to the third is 8. And if x is negative, 2 to the negative 1 is 1/2. 2 to the negative second is 1/4, and so on and so on. So what we see is, we get point 0, 1. Fine, I'll do a good job. So we get this point here, and this point here, and this point here, and then this point here. It kind of looks like this. This is your usual exponential shape. It's getting very big, very fast. If you graph this on something like Desmos, where it actually kind of gives you the scale. In fact, let's go ahead and do that. You guys, I definitely recommend everybody get familiar with Desmos if you haven't already. It is definitely a nice tool to use. But I just want to point out, if you graph something like this on Desmos, it has the right shape, but if you zoom out, you might start to be able to convince yourself that there's a vertical asymptote. There is not a vertical asymptote. I know it gets steep super duper fast, and like it looks like, well, James, that really looks like a vertical line. I'm like, I know it looks like a vertical line. Sorry, and I'm kind of zooming over, right? It kind of looks like, okay, maybe we never get past 10. You definitely get past 10 because, well, if you look at the function here, right, x can definitely be 10. X is allowed to be any number, really. So I really, really want to stress that exponential functions like this, where the base is some constant and the exponent is x or some variable, they don't have vertical asymptotes. They do get steep very, very fast, but they do not have any place where they're undefined. So this is kind of the general shape. And this is the general shape of any exponential function. So if I wanted to graph, something like y equal to 3 to the x, it would look virtually the same. It'd be a little bit steeper, right? I'd have the point, I still have the point 0, 1, and then I'd have the point 1, 3. Now, do these graphs look the same when I graph them? Yeah, pretty much. Because all exponential functions kind of have the same shape. If you graph them on the same coordinate system, like if I also graphed, say y equal to 10 to the x, well, okay, then I have to make it look steeper. So then it's gonna be like, okay, right, it's gonna get bigger way faster. This is gonna be the point. Still gonna get the point 0, 1, also gonna get the point 1, 10. You don't need to plot this other point, but sometimes people do to kind of differentiate between them. So the other thing, not the other thing. So we can also have bases that are less than 1, still positive. I should mention, there's a lot of things I should mention. When you have an exponential function, the base can't be negative. So what I mean by that is you can totally have something like this. -3 to the x. Because that negative is on the outside of the function. And so what it's going to do is it's actually going to flip over the exponential function, meaning it's going to take your 3 to the x, which looks like this, and it's going to flip it over the x-axis. So y equals -3 to the x. Looks like that. But better. That's the point 0, -1. And here's the point 1, -3. Yes, I know my scale is terrible. I do want to mention, though, this is not the same as y equal to, say, -3 to the x. This we don't deal with. The reason we don't deal with this is because if your base is negative, there's going to be a lot of values of x where this expression is undefined. Right? Like -3 to the 1/2 power is the square root of -3, and we don't take square roots of negative numbers, right? They're not real. So we don't deal with negative bases. You can put a negative in front of the function and be fine, but you can't have a negative base. You also don't want 0 as a base because 0 to the x is just not interesting. You also don't want 1 as a base because 1 to the x is just a constant function. So our bases, in fact, I'm done with this. We're talking about exponential functions. Maybe they use the letter b, but they use the letter a for some dumb reason. So f of x equal to a to the x is an exponential function. But then we specifically require that a is greater than 0. And we also usually say that a is not equal to 1. Because 0 is a problem, negative numbers are problems, and 1 is not a problem, but not really exponential, right? 1 to the x is just always 1. So all of our examples so far have been where the base is larger than 1. If your base is less than 1, for example, if you have f of x equal to, say, like 1/3 to the x, well, that's going to look kind of like all the other graphs, except it's going to be turned around. The way I kind of think about it is for something like 3 to the x, if your x values are getting larger, your y values are getting larger, right? 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 8, right? They get really big as x gets bigger. And as x gets smaller, the y values get smaller, right? If x is -1, you get 3 to the -1. If you get -2, y is 3 to the -2, which is 1/9. So you're getting still positive things, but smaller and smaller and smaller fractions. But when you have a base that is less than 1, you have the reverse relationship, or the opposite relationship, I should say. If x is big, the y values are going to be small. Right? If x is 1, y is going to be 1/3. If x is 2, 1/3 squared is 1/9. If x is 3, 1/3 cubed is 1/27. So as the x values get bigger, the y values actually get smaller. But then if x is negative, 1/3 to the -1 is 3. And 1/3 to the -2 is 9. Right? That negative power gives you a reciprocal. 1/3 to the negative second is the same as 3 squared. There's a number of ways you could see that. So it looks like that. And what's interesting is, well, one of the things that's interesting is this is actually the same as 3 to the negative x, which is that reflection in the y-axis. So exponential functions have this look. And what I want to say about them is that, well, there is something that is kind of important. So if I said, okay, here's your very, very general exponential function, y equals a to the x. Since it's increasing from left to right, we know that our base a is greater than what? Anybody? 0 is a good guess, but I will point out that this one here had a base that was 1/3 and it went down from left to right. So what's another number that might be where that we change? Right, 1 is the place, right? So if your base is less than 1, you're going to go down from left to right. If your base is larger than 1, you're going to go up from left to right. And so we can actually say some things about this. If we look at this, we can see, this is where I kind of wanted to kind of, yeah, that the limit as x goes to infinity of a to the x is equal to infinity. And we can just see that from the graph, right? Look at the graph. As x goes this way, the y values go this way, right? Because we're going this way. And the limit as x goes to negative infinity of a to the x is equal to, well, now we're going this way. So what are the y values getting closer and closer and closer and closer to? Zero. And then you can also say, let's do this. So you can either, and there's a couple different ways to write this. You can either say, if I've got y equal to a to the x where a is less than 1, or if you just, so that's not the way he did it in class though. So I'll do it the way he did it in class, which is he said, if you've got y equal to a to the negative x. So again, if you put a negative on your exponent, well, interestingly, putting a negative on your exponent, you can write it like this. That's a to the negative 1 to the x. But a to the negative 1 is 1 over a. And now here's the thing. If a is bigger than 1, 1 over a is less than 1. So this graph has this look, right? We just said if the base is less than 1, it's still positive, then it goes down from left to right. Because bigger powers here, right? Like if x is 2, 1 over a squared is going to be a smaller number. And 1 over a to the 10th is going to be even smaller because a is big, 1 over a is small. So if you look at this one, you can say, okay, the limit as x goes to infinity of this graph, which is y equals a to the negative x, is going to be 0, because as we go out this way, the function is getting closer and closer and closer and closer to 0. And the limit as x goes to negative infinity of a to the negative x. So as we go that way, the graph gets really, really large. So I just want to point out that the slight error that was in the lecture notes was that these limits were stated to be true if a was greater than 0. That's not actually the case. These limits are true if a is greater than 1. And I just want to make sure everyone's really, really clear about that. what else to say? The only other thing to really kind of make sure everyone, and I guess maybe I should say this first, oh well, is just make sure everyone's all right with the exponential rules. So there's a few things that I think everyone should be aware of. We can say that this, so again, right, if your base A is greater than 1 and not equal to 0, we have the following rules. We can say that A to the 0 is equal to 1. We know that, right? If you have a non-zero number raised to the 0th power, it's going to be 1. What else do we have? We have the additive law of exponents. A to the x times a to the y equals a to the x plus y. And we use that a lot. Like, 2 cubed times 2 squared is just 2 to the 5th. And then we also have the same rule, but written as a fraction. A to the x divided by a to the y is a to the x minus y. This really is just this rule combined with this rule, that a to the negative x is equal to 1 over a to the x. Right? That's the same. If you combine this with that, or sorry, yeah, no. Basically, I can rewrite this rule as a to the x divided by a to the y is equal to a to the x times a to the negative y. And then you add the exponents, so you get a to the x plus y, which is just that. So really, this rule is kind of extra, but it's still nice to know it. Yeah, I mean, and there's also a to the x to the y equals a to the xy. So like this one, I think of like, if you got 2 to the 3rd to the 4th, that's really 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd. Then that's 3 2s times another 3 2s times another 3 2s times another 3 2s. That's 12 2s. I'm not going to write 12 2s. I'm going to write 2 to the 12th. So we just multiply the exponents. What else to say about exponential functions? Oh yeah, we should say one more thing. So there's also the everyone's favorite number, maybe not, but a very important number, the number e. What are we talking about, James? It's a letter. No, it's a number. E, approximately 2.7. When I graph f of x equal to e to the x, wow, let's try that again. I should be using my other pens. I want to just, I've got a bunch of pens that have like a little bit of ink left in them. I should try to like use up. Let me turn them all over actually. There we go. So I'm going to try and graph this kind of nicely because I want to make an observation, even though I know it's a little early for it. So so if I plug in 1 for x, e to the 1 is about 2.7. So I'd be like about right there. Yeah, we'll get there in a second. So there's e to the x. And when I graph this, in fact, let's go back to Desmos for just one moment. Sure. So just to let you know, let's go back to the home so it doesn't look expressive. So there's 2 to the x, and there is 3 to the x. And then in between them, right, 2.7 is in between 2 and 3. It's a little closer to 3. E to the x is in between them. And that's kind of true actually for any exponential functions, right? The bigger the base, the steeper the function is going to grow, or the faster it's going to grow. The smaller the base, whoops, let's go back there. It's not going to grow, the smaller bases don't grow as fast. But then they switch, right? If you look over here on the left, the smaller bases also don't get small as fast, right? In fact, I kind of think of the bigger base as always doing things faster. So the bigger base, 3 to the x, gets bigger faster as you move to the right, gets smaller faster as you move to the left. The smaller base, 2, doesn't get big as fast, right? It grows more slowly and also decays more slowly if you're going to the left. That's a nice way to think about it. But I really am showing you this to see that, oh yeah, e to the x is in between those two, but it's just another exponential function doing its exponential thing. What else to say? For all these exponential functions, so for f of x equal to a to the x, again, a is not equal to 1, a is greater than 0. There are a couple other things we should say. The domain is everything. The range is all positive numbers. And we have a horizontal asymptote at y equal to 0. Depending on which way it is, it's either to the left or the right. Now, no one's really going to ask you about that, but right, if it's increasing like this, it's your horizontal asymptote y equals 0 to the left. If it's decreasing like some of our other examples, it's y equals 0, but it's to the right. But again, you still get y equals 0 being a horizontal asymptote. There's something else I had intended to say about this, which is the following. So your teacher definitely talked about, or at least wrote in his notes, about how E is defined. This is not super duper. I mean, it is actually very important. I don't know if it's super important that you know it, but I'm going to show you. And there's actually two ways of writing it. One way of writing it is that E is equal to the limit as x goes to 0 of 1 plus x to the 1 over x power. Another way of writing it is that E is equal to the limit. I usually use a different letter than x. People often use n or h. Limit as n goes to infinity of 1 plus 1 over n to the nth power. If you think about it, these are really kind of the same. If you think about x equaling 1 over n, then this is totally the same as that, right? If you replace 1 over n with x, okay, that's 1 plus x. If you replace, well, if x equals 1 over n, then nx equals 1 and n equals 1 over x. So 1 over n becomes x, n becomes 1 over x, and if n goes to infinity, x, which equals 1 over n, goes to 1 over infinity, which is 0. So these limits both represent the same thing. And it's kind of neat. In fact, let me show you one test. So Desmos is a great tool. I think you can see a lot of cool things. One thing you can totally see are limits. So if we actually plot either one of these, so if we do like, let's do the second one. Let's do 1 plus 1, whoops, not 1 equals 1 plus 1 over n to the nth power. Come on. I don't want a slider. No slider. Oh, I need a y equals. I'm like, why am I not getting a graph? There we go. So if you look at this, so right, it looks like there's a horizontal asymptote. If I graph y equal to e, there's the horizontal line y equal to e. Look, oh yeah, that purple graph is getting closer and closer and closer to the value of e, right? They look like they've essentially become the same thing. They're not exactly the same, but they do get very, very close to each other, right? So you can see, oh yeah, this expression as n gets very, very large. In fact, now I do want to add a slider. Give me back my slider option. No, this won't do it to me anymore. Oh well. Oh well. Anyway, it doesn't really matter. But we can also see the other one has, well, not exactly the same behavior, but similar behavior. If you look at y equal to 1 plus x to the 1 over x, I guess, sure. So now, like I know I'm getting a lot of graphs here. Let's turn some things off for a second. You look at that one, this graph, this red graph, as you approach 0, the y values do look like they're going right towards e, right? That line there is y equal to e. Now, if you look at it, it's actually not defined there because you'd have 1 over 0 in your exponent, which is undefined. But you can totally see, oh yeah, from the left, from the right, it's coming about towards that e value from the left side. It's also coming towards that e value. So it definitely is true that these limits are what they say they are, that they are equal to them. I'm sorry, there's something. Sorry, whenever I share my screen, I usually forget to open up the chat, so I don't see the chat. Is that because as the number gets bigger and bigger, the fraction is close to close? Sorry, Mark, I'm not sure what your question's in reference to because I didn't see when you wrote it. So here's what I'll say about both of these limits. Both these limits. Let me stop sharing my screen here. Both these limits are what are called indeterminate form. They're both of a form that's what's called a 1 to the infinity form. So if you look at this limit, let me erase some of these things here. If the person who wrote their question wants to clarify, I'm happy to address it. I don't know what the context is. So if you look at this here, as x goes to 0, this is getting closer and closer to 1. It's not actually 1, right? Because x isn't ever actually 0. It's just getting super duper duper close to 0, like a limit does. Same idea here. As n gets really, really large, 1 over n gets very, very small, and 1 plus 1 over n gets very, very close to 1. And now both of these, the exponent's getting very large, right? N's going to infinity. 1 over 0 is also going to some sort of infinity. So you have what's called a 1 to the infinity. Now you might think, okay, what's written next to x equals 1 over n? That's n times x equals 1, right? I was solving for n there. So I multiplied both sides by n and got n times x equal to 1. And then I divided both sides by x to get n equal to 1 over x. To show you that you can go from this to this. So what I was saying is you might accidentally convince yourself that 1 to the infinity power is equal to 1. Which would make sense. Like, well, 1 times 1 times 1 times 1 times 1 forever is just 1. But the thing is, it's not actually 1. It's 1 and a little bit more. And if you have 1 and a little bit more raised to a very large power, it actually isn't equal to 1. And that's where this special number e actually comes into play. You might have seen this before. Sorry, my chair is in the wrong place. You might have seen this before. You might have seen it with me. Maybe not. I don't know. Now I feel like we should talk about it. It is good to have context, and then we'll get to the law. Yeah, okay. So here's one way you could think about it. And I've probably said this. If you stop me if you've heard this one. Well, don't really, but do this the quick way though. Let's say I lend you $1. I'm a nice guy. But I charge you 100% interest. So not that nice. And I want to know how much money am I going to get at the end of 1 year. But it depends on how often we compound the interest. So here's my compound interest formula. The amount of money is equal to principal times 1 plus the rate divided by the number of times you compound it to the nt power. That's your compound interest formula. In this case, everything is 1 pretty much. The principal, right, the amount I'm lending you is $1. The interest rate is 100%, which is 1 as a decimal. And the number of years is also 1. So here's my formula. 1 plus 1 over n to the n. And you can see that, okay, well, if we let n equal 1, I'm going to get, well, 1 plus $1, I'm going to get $2. And the dollar I lent you plus the dollar of interest I earned. But if we compound it twice, well, if I compound the interest twice, that means you break up the interest into equal amounts in less time. Right? So if I compound the interest semi-annually, after 6 months, I'm going to get half of the interest. So I'm going to get 50% interest on $1, so that's 50 cents. So then I have $1.50. That's after, sorry, I wrote that kind of terribly. But then I'm also going to say, well, now on my $1.50, in the next 6 months, I'm also going to earn 50% interest, which is going to give me 50% of $1.50, right? Because it's compounding the interest. is 75%. So I'm going to get another, sorry, 75 cents. So I'm going to get $1.50 plus 75 cents, which is $2.25, which is exactly what you get if you plug in 2 here, right? 1 plus 1/2 squared is 3/2 squared, which is 9/4, which is 2 1/4. So you can keep doing this. You can say, well, okay, what if I compound it, 4 times per year? Well, I get 1 plus 1/4 to the 4th power. And I didn't plan ahead to do this, so I didn't actually calculate that. It's going to be 1.25 to the 4th, which is 2.44. No problem. So, right, if I compound the interest 4 times per year, I get $2.44. So you can kind of see already, well, first of all, if you got 1 plus 1 over n to the n, the smallest it's going to be is 2, right, when n is 1. But as n gets larger, this value actually is getting larger each time. So there's no way 1 plus 1 over n to the n, as n gets really big, could be 1, right? It's got to be actually bigger than 2 because it's getting bigger. And if you get really, really big, like if n is 365, you get numbers that are very, very close to e, right? You get 1 plus 1 over 365 to the 365th power, which I used to know, but I will just do it here. 1 plus 1 divided by 365. Oops, not 356. To the 365th power is 2.71456 about. So here's the thing. E is kind of the limiting amount. If you compound if I took this example, if I lent you this dollar and charged you 100% interest and I compounded interest continuously or an infinite number of times in that year, you would owe me E dollars. So hopefully that makes it a little more tangible. Here's what I would like to say about E, specifically E to the X. I think I've drawn this pretty well. So this is E to the X. Let's look at this tangent line right here. Well, that tangent line, I've drawn it decently. That pretty much looks like it's y equals x plus 1. And it is. Specifically, to answer, so I'll get to that question in 1 second. The slope here is 1 at that point. Or the slope of the tangent line is 1 at that point. And what's kind of really, really special about this function e to the x is that kind of thing is true actually at any point, in that the slope of the tangent line is equal to whatever the y value is. So right here at that point, 0, 1, the y value is 1, the slope of the tangent line is 1. At this point up here, which I know is kind of a weird point, but it's the point 1 comma e. If I could draw the tangent line perfectly, the tangent line there has a slope of e. Which means if the tangent line slope is always equal to the y value, what it actually means is that if your function is e to the x, your derivative is also e to the x, which is true. This is kind of one of our favorite functions to differentiate because its derivative is literally itself, which is kind of a great thing. But it makes sense if you look at the picture, right? Here, the slope of the tangent line is very small and the function is very small. And as you get bigger, oh yeah, the slope of the tangent line is getting more positive and the function is getting more positive. Now that's not always true for any kind of picture, but it is true for this specific picture, in that the slope of the tangent line is always exactly the same as the y value of the function itself. Who knew? There was a question, is E always a limiting amount or only for the specific situation? It's kind of for the specific situation. It's specifically for this limit. Well, either of these limits. The limit as n goes to infinity of 1 plus 1 over n to the n, or the limit as x goes to 0 of 1 plus x to the 1 over x. Both of these are equal to e. There are other situations where you have expressions that are kind of similar in nature, but not exactly the same, and then the limit might end up being e squared or e to the negative third or something like that. But I wouldn't worry too much about it. Really, we're mostly building this context so that we can get to talking about the derivative. We are also going to talk about exponential growth and decay, so there is some of that we will have to deal with. Mostly, we want to be able to take derivatives of these functions. And this, I will tell you right now, the derivative of e to the x is in fact e to the x. Yeah, let's see where we at time-wise. I will say in your book, they do give, they give a loose, they're a little loosey-goosey with their derivative of e to the x. But I would encourage you to remember this. If you're like, why is the derivative of e to the x e to the x? Oh yes, because literally the slope of the tangent line is the y value of the function. Okay. I did also see a couple homework problems where they wanted you to do some solving of some exponential equations. Like, I don't know, maybe, I feel like I saw something similar to 1/2 to the x equal to, I don't know, 8 to the 5th or something like that. If you see an equation like this, the goal here, or one way of tackling it, is to write both things as powers of the same base. So 1/2 is 2 to the negative 1. And 8 is a power of 2 as well. That's 2 to the 3rd. So then you can say, oh, 2 to the negative 1 to the x, you can multiply those powers together. So 2 to the negative x equals 2 to the 3rd to the 5th is 2 to the 15th. And then once you get to a place where the bases are the same, you could either take the log of both sides, which seems like extra work, or just say, well, if the bases are the same, the exponents have to equal each other. That's how you could solve an equation like that. That's often the intent behind questions like that, is that you want to kind of write them both as powers of the same base. Let's see. Trying to see if there's anything else. Yeah, most of you do this homework. Okay. Look at one other problem. Yeah. And then, so I'll look at one other problem that's similar to a home problem, and then I will start talking about logarithms for the last 20 minutes here. So the other question I saw, which I thought was kind of interesting, I'll write one similar, was something like, I don't know, let's say 3 squared equal to x plus 4 squared. And they want you to solve this. Now, there's a couple ways you could go. To me, it seems like the easiest way to go would be to say, take the square root of both sides. Square root of 3 squared is 3. Square root of x plus 4 squared. Well, now here's where we have to be a little bit careful. Square root of x plus 4 squared actually isn't just x plus 4. It's actually the absolute value of x plus 4. Really, I'm kind of showing the extra steps where you say, oh, I know if I take the square root of both sides, I get my variable thing equal to plus or minus the other thing. That's what's happening, right? I'm taking the square root of both sides, I'm getting x plus 4 equal to plus or minus 3, which makes sense, right? It totally would be great if x plus 4 was equal to 3, because 3 squared is equal to 3 squared. But it would also be totally perfectly fine if x plus 4 was equal to negative 3, because negative 3 squared is still 9, which is equal to 3 squared. So my answer here would be x equal to, I'm going to subtract 4 from both sides, negative 4 plus or minus 3. So x could be negative 4 plus 3 or negative 4 minus 3. That is certainly one way you can solve it. It's probably the easiest way to solve it. The other way you could solve this, which is a little bit more work, would be to actually multiply it out, bring it everything to one side. It's okay, 9 is equal to x squared plus 8x plus 16, and then bring everything to the right so that 0 equals x squared plus 8x plus 16 minus 9 is 7. And then you factor and you get x plus 7 times x plus 1. And then you get x equal to negative 7 and negative 1. Oh, it's the same. So there you go. Oh, that's cool. Good to know. Thanks, Marshall. All right, so let's talk about logarithms for a tiny bit here. Well, so logarithms and exponential functions are inverse functions, and they have all the properties the inverses have. So if your function was, say, f of x equal to 2 to the x, the inverse function would be g of x equal to log base 2 of x. And they have the symmetry of inverse functions, which is that they are reflections of each other across the line y equals x. So if here, and I'll try and draw this somewhat nicely. So here is our 2 to the x. And well, the nice thing about inverse functions is they literally, right? How do you find an inverse function? You interchange x and y. They literally have all the x and y coordinates interchanged. So if your function f has the points, like I've got the points, I've graphed specifically the points -1, 1/2, and 0, 1, and 1, 2. My inverse function is going to have the switched points. It's going to have the points 1/2, comma, -1, and 1 and 0, and 2, 1, and 4, 2, and 8, 3, right? Because if you take log base 2 of 8, you're saying 2 to what power equals 8? Oh, that's 3. Taking log base 2 of 1, you're saying 2 to what power equals 1? Oh, that's 0. So we're just taking these points and putting and reflecting them across the line. Y equals x. So instead of 0, 1, I get 1, 0. Instead of 1, 2, I get 2, 1. Instead of -1, 1/2, I get 1/2, -1. And so instead of getting a horizontal asymptote at y equal to 0, well, I interchange x and y, and I get a vertical asymptote at x equal to 0. Now, I know that for logarithms, we often, just like for exponential functions, we say that the base can be anything that's positive and not equal to 1. So if I'm talking about more generally, and I'm looking at, say, f of x equal to log base a of x, the base should be greater than 0, and the base should be not equal to 1. But I'll also tell you, typically, when you're dealing with logarithmic functions specifically, it is almost always going to be the case that a is going to be an integer number or e. Yes, you're totally allowed to have other things, like you're allowed to have a base that is the square root of 5, which seems really weird, or 1/3, or anything else that's kind of atypical, but we don't usually. So most logarithmic graphs, if they kind of don't do this weird thing down here, they'll have this sort of look. Where you've got the point 1, 0, you've got a vertical asymptote at x equals 0, your x-intercept is 0. And it's increasing, right? As we go from left to right, the function is getting larger and larger and larger and larger and larger. I will just very briefly mention, you could have a base that's wonky. Someone could ask you at some point in your life to say, I would love you to think, well, I should maybe write something. And this is y equals a log base a of x, where a is greater than 1. But if I said I want to graph log base 1/2 of x. Okay, well, that's when things get flipped, turned upside down. Like, take a minute, just sit right there. No, just kidding. Okay. So, for exponential functions, when your base becomes a number less than 1, you flip across the y-axis. For logarithmic functions, which are the inverse, you switch x to y. When your base becomes a number less than 1, you flip across the x-axis. Or you can just plug in some values. Still, when you plug in 1, log base 1/2 of 1 is going to be 0. But now if you pick a number like, I don't know, say 2, what's log base 1/2 of 2? Let's see, 1/2 to what power equals 2? Oh, that's the -1 power. 1/2 to the -1 equals 2. So when I plug in 2 for x, I get -1 for y. And when I plug in 4 for x, I get -2 for y. And then if I plug in smaller values, if I plug in 1/2, log base 1/2 of 1/2 is equal to 1. So again, I don't want to spend more time on this, so I don't really think it's that important. But I just want to point out that if someone gave you a dumb base that was less than 1 and still positive, your logarithmic graph would get flipped over the x-axis from this to that. But no one's going to ask you about that, so I really should not say anything else about it. Oh, let me stop. So, interestingly, logarithmic functions, it could be y equal to log base 2 of x, or y equal to log base 10 of x, where we don't write the base, right? That's base 10. Or y equal to the natural log of x, where we don't write the base because it's easier to write base e this way. And this is base e. This is really just about laziness and trying to save some ink. Right? Back when they were typesetting these things, they're like, I don't want to write log base e of x every time I have to do that. I don't want to typeset that every time I have to typeset when I'm printing this book. We're going to abbreviate these things to make it easier because they get used so much. Specifically, these two, log base 10 and log base e. So these are our abbreviations. But what I was going to say about these is all of these have a vertical asymptote at x equals to 0. All of them have a domain that is 0 to infinity. All of them have a range of everything, which, just want to point out, the domain of this function is the same as the range of the exponential function. And the range of this function is the same as the domain of the exponential function, which is always true about inverse functions. Their domain and their range are interchanged. Okay, and let's talk about some, I'll leave that for a second. Let's talk about some log rules, because I imagine these will come up. So here are the rules, and they are very related to the exponential rules we talked about earlier. We have the, I don't want to call it the product rule because there's a, right, we know the product rule is a rule for derivatives, but there is the product rule for logs, which is that if you have the log base a of any product x times y, you can write it as log base a of x plus log base a of y. And there's also a quotient rule for logarithms, log base A of x divided by y is log base A of x minus log base A of y. We also have a power rule for logs. Log base A of x to the pth power is equal to p times log base A of x. And then there's also the change of base rule, which I think you guys want to know. If you have log base A of x, you can write this as pick whatever base you like, log base b of the top thing divided by log base b of the bottom thing. I find this especially useful if you're trying to evaluate something where you can see, for example, I don't know, log base 4 of 1/8. Sure, we could so there's a couple ways you could tackle this problem. One way would be to say, okay, let's say it's equal to x, and then say 4 to the x equals 1/8, and then rewrite both sides as powers of 2. 4 is 2 squared to the x. This is 1 over 2 cubed. So we've got 2 to the 2x equals 2 to the negative third. So 2x equals negative 3. So x equals negative 3/2. That's one way you can certainly tackle this problem. But another way to do it is to use the change of base formula. Recognize, oh, 4 and 1/8 are both powers of a common base, 2. So rewrite this as log base 2 of 1/8 over log base 2 of 4. And then log base 2 of 1/8, you can even use the quotient rule for logarithm and say that's log base 2 of 1 minus log base 2 of 8. And we know that log base 2 of 4 is 2, because 2 to the second power is equal to 4. Okay, in the numerator, log base 2 of 1 is 0, because 2 to the 0th power is equal to 1. And log base 2 of 8 is 3, because 2 to the third power is equal to 8. And look, we get negative 3/2. So the change of base rule is a good rule, or change of base formula, whatever you want to call it, is a good formula to be aware of. Yeah. So I know we haven't. I feel like today we haven't done like a lot of problems. It's been more of me like explaining things, which I don't love. Not that I don't love explaining things. I don't love that it's like that more problems. Don't worry. I promise we'll do more like problems as we go on. I just felt like there are a few things we had to make sure we were all kind of on board with. So in a similar way, I talked about the derivative of the exponential function. I'm also talking about the derivative of the logarithmic function. Now, we will also talk about how to find the derivative of the exponential and the logarithmic function in more of the standard ways. But I feel like it's nice to have an idea of what's going on here. So let me try and draw this very, very precisely. So let's see. I know that when I plug in 1, I get 0. I know that the natural log of e, right? I'm graphing the natural log function. So y is the natural log of x. If I plug in e, the natural log of e is equal to 1. Because natural log of e is the log base e of e to the first power is equal to e. So I plug in e, which is about 2.7, I should get 1. So I wrote right there. Okay, and then 1 over e is about 0.36. Like that. Okay, sure. So here's my graph. Okay. And then here's kind of an interesting thing to think about. If you look at the inverse function, e to the x, the slope of this tangent line here, since it's 1, is the same as the slope of that tangent line there. It's really the reciprocal, but the reciprocal of 1 is 1. And that's actually kind of an interesting thing in that, right, like if you take, let me erase this for a second. If you take kind of any point on the graph here, so like here's the point 1 comma e, where we talked about before how the slope there is e, right? We did. Well, the slope over here in this kind of related point is the reciprocal, right? This slope is super steep. This slope is not super steep, it's super shallow. So the slope there is actually 1 over at the point e comma 1. So here's what's kind of really interesting. For e to the x, the slope is the y value. For natural log of x, I should say the slope of the tangent line is the y value at any particular point. But for, and I feel like I've drawn this kind of in a very messy way here, and I apologize for that. But for the natural log function, the slope of the tangent line is, well, it's not, it's the reciprocal of what the x value would be, because it's the reciprocal of what the y value would be over here, right? Because it's the slope here is the y value, the slope here is the reciprocal of that y value, but the x and the y value have changed. So the slope here is just 1 over e. And in general, the slope of the tangent line is just 1 over whatever the x value is. So here's kind of a very, very kind of hand wavy, but very true way of seeing that the derivative of the natural log of x is in fact 1 over x. And if we look at this, we can even graph it, right? And I wish I had graphed this more vertically, but we can graph 1 over x. I don't care about the left-hand part. I'm just going to graph the right-hand part. Okay, so let's think about it. Over here, before we get to 1, the slope of the tangent line is super steep and positive. Hey, look, the function is super positive. And then as we get closer to 1, like say maybe right there, the slope of the tangent line is still positive, but not as steep. Okay, well, as we get to, like right here, the value is still positive, but not as positive. When we get to 1, the slope of the tangent line is 1. When we get to 1, the y value is 1. And as we go further to the right, my slopes are getting less and less and less positive. And here, as we go further to the right, my values are getting less and less and less positive. So it is, in fact, true, the derivative of the natural log of x is 1 over x. And there are lots of ways we're going to talk about this, but it's really kind of, I think, a good idea to have a graphical concept of what's going on. Like, oh yeah, natural log looks like this, and its tangent lines go from having very, 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 very positive slopes to having very, very less positive slopes, right? It's still positive, right? The slope of the tangent line is always positive, but it goes from very positive to very, very small, getting closer and closer and closer, but never equal to 0. Okay.